Jnanam Paramam Dhyayam. Knowledge is supreme.
We are now to the end phase of our tutorials, and this tutorial remaining tutorials will be more focused on Clash-Gordon coefficient and Wigner-Eckardt theorem. And so there will be again the set of 5 problems, and this tutorial you will I will just give you an outline and you can just fill in the gaps and solve each and every steps, because Clash-Gordon coefficient has been discussed in the class and Wigner-Eckardt theorem will be following in the following lectures. You will see how Wigner-Eckardt theorem can be used, and these 2 tutorials will actually give you a flavor of how powerful is the raising and lowering operator and how these can be used to obtain the Clash-Gordon coefficient. And let us now start with the first tutorial, first problem of this tutorial. And as you have already seen in your regular class that Clash-Gordon coefficient for a system of 2 particles of spin of angular momentum 1, half and half, how it can be obtained. So, for half and half you had 4 cross 4 matrix that you have to obtain, and here what we are going to do is, so this half is discussed in the class, right. And on the similar line actually you can calculate the first problem, that is you have to calculate 1 cross half when J1 is equal to 1 and J2 is equal to half. So, when J1 is equal to 1, M can take values, M1 can take values 1, 0 and minus 1, and M2 can take values half and minus half. Okay. And you will see how easy it is to calculate these Clash-Gordon coefficient. Once you get the idea how to proceed, then some of the terms you can just evaluate by orthogonality condition. So, we start with J1 is 1, J2 is half, then capital J or J takes values from J1 minus J2 to J1 plus J2. So, in this case our J can take value half and 3 by 2, agreed. And what will be the value of capital M? Capital M will also take value from M1 minus M2 to M1 plus M2. Okay. So, here you can see that you are writing this coefficient in terms of a coupled and an uncoupled basis. So, when you are calculating, let us write the uncoupled basis first. So, the state of the system, state corresponding to J1 and J2, that is J1 as 1 and J2 as half, what do we obtain? How do we write the state of the system? J1, J2, M1, M2. And please note that there are various ways of representing this states. Sometimes you see people write it as J1, M1, J2, M2. The order is not so important, but you need to remember what is your whatever you are writing, whatever form or whatever order you are writing, you have to stick to that order. So, J1, J2, M1, M2 is the uncoupled state. So, this is an uncoupled state or the uncoupled basis, and the uncoupled basis is a reducible state, or it can be called as a reducible state, and the state corresponding to J okay, can be written as, that is J is half and 3 by 2, can be written as J comma J1 comma J2 comma J comma M. So, in your lecture you have seen that it is denoted by a curve bracket. Okay. So, this is the angular bracket. So, this is a coupled basis or the coupled state, and these coupled states or coupled bases are irreducible bases or irreducible states. Okay. And before we go ahead, let us check the dimensionality of these two bases. Are they dimensionally correct or equal? Okay. So, here I can write for J1 is equal to, so J1 cross, so let me write 1 or J1 cross J2 is nothing but 1 cross half. This is what we are evaluating. So, for 1 cross half, what will be the dimension for J1 is equal to 1, the dimension will be 3, and for J2 is equal to half, the dimension will be 2. This is nothing but 6. Similarly, I will find out the dimensionality for J when J is half and when J is 3 by 2. So, when J is half, dimensionality of J will be 2, and when J is 3 by 2, dimensionality is 4. So, this is nothing but 2 plus 4, that is 6. So, dimensionally you can see that the two dimensions are matching. So, in general, if I want to write the dimensionality of the coupled and the uncoupled bases, one can equivalently write the dimensionality or dimension is 2 J1 plus 1 into 2 J2 plus 1. So, this will be a product, okay, but this is a tensorial product, remember, it is not a direct product, it is a tensor product. So, the tensor product is equivalent to, this is the sum, the direct sum from J is equal to J1 minus J2 to J1 plus J2, which is 2J plus 1. This is what we have done in this example. J1 cross J2 is equal to J. So, I can rewrite actually this in the form. Here what I mean is J1 J2 is equivalent to direct sum of J1 going of J1 minus J2 to J1 plus J2. Sorry, this will not be there because you do not need a mod when you are taking the sum, only when the difference. So, 2J plus 1. This you need to remember, this is the first step in which you will understand actually how you can compare the reducible and irreducible states. So, you should have the idea how these dimensionally match. Okay. So, the uncoupled bases are reducible bases or the reducible states, and the coupled bases are irreducible states. So, with this now you need to go a step ahead. Okay, before we go to the table or what you call as Clash-Gordon coefficient or CG coefficient table, you prepare a table and write the coefficient, that is more convenient to understand and look and interpret also. So, before we go to that table, let me tell you some places J1 and J2 in the state is suppressed, and we write it as J comma M for the coupled state and M1 M2 for the uncoupled state. This is how these states are represented. So, when I write J M M1 M2, and if I take the reverse of this, that is I do this the other way, this will be nothing but the complex conjugate of this. But if your coefficients are real, there will be no change. So, they are equal, the complex conjugate as well as the this number what you obtain is the same. So, you will see how this table is prepared and how one can actually write in a beautifully in the block diagonal form. So, let us go to the table part. So, in this table part, to obtain, this is the point you should remember, to obtain the CG coefficients, what we will do is we will require or we will use ladder operator. So, you just recollect J minus or J plus when operated on a state say J comma M, it will give you C minus or plus, that is this is the CG coefficient that you will obtain, and now you know actually how to obtain these CG coefficient J M minus or plus. Okay. Similarly, if the ladder operator is operated on M1 M2, so when I do this J1 minus plus J2 minus M1 M2, so once it will operate on M1 and the other time on M2. So, I will have C1 plus minus, so it will be same for plus and minus component. This we will be using, and I will show you one example and then the remaining you can fill up the gaps. So, C1 will give me M1 plus minus comma M1 comma M2 plus C2 plus minus M1 M2 plus minus. So, the state will be either lowered or it will be raised by a factor of 1 depending upon which operator you are operating. J plus will raise the state by 1 and J minus will lower the state, that is M by minus 1. So, with this now you can, I will make a table. So, we will do some working on this page, but when I prepare this table, what I can do here is I will have horizontal. Okay. So, here what I am doing is I will write the CG coefficients. So, this will be M1, M2. So, these are the reducible states and Jm are the irreducible states. Okay. And corresponding to these states, we will have to write the corresponding coefficients. So, as we have seen in the previous, like J1 is 1 and J2 is half. So, J can take value half and 3 by 2 or 3 by 2 and half, whatever. Similarly, M1, M2, if I want to write them in terms of the states, and M can take values, here I will have M can take values 3 by 2, half, minus half and minus 3 by 2. So, 3 by 2 will have 2 states, 3 by 2 and minus 3 by 2, half will give me 2 states 1 and minus half. Similarly, for M1, M2 you can have different states. So, this let me write this for the uncoupled state. I will have this, I can write it as 3 by 2, 3 by 2. So, what we will do is we will write these states in the decreasing order of M. So, 3 by 2, 3 by 2 will be the first term in the column, and the next one will be 3 by 2 half, then comes half half, then comes half minus half, then half, 3 by 2 and half, minus half, and minus 3 by 2, sorry 3 by 2 and minus 3 by 2. So, decreasing order of M. So, 3 by 2, half, half, minus half, minus half, minus 3 by 2. So, you can have 6 such combination. Similarly, for J1 and J2, I mean M1 and M2, we will have combinations. So, M1, M2, let me rewrite it here only. So, M1 and M2, I will have M1 can take value 1, 0 and minus 1, M2 can take value 1 and minus half. So, this will be 1 half, this is the highest state which can be achieved. Okay. The second will be 0 and half, then third will be 1 and minus half, then fourth you can have minus 1 and half, or you can have 0 and minus half, or you can have minus 3 by 2, sorry minus 1 and minus half. So, that will give me minus 3 by 2. So, whatever I have written it here, it looks very clumsy. So, when I write it in the form of table, it is very clear, very neat and very much understandable. That is the reason why I showed here that when you write the state, it is very difficult to evaluate this way, but now when you look this and rewrite in the form of table. So, here I write first state, highest state, then I have 1, 0 and half, then I have minus. So, I will write in the order of decreasing M, 1 and minus half. So, there are various ways in which you can group these states. So, here my intention is to group the states in terms of decreasing order of M, okay, and you will in a minute you will understand why is this choice being taken. So, this is 3 by 2, 3 by 2, this is the highest state, then I have 3 by 2 half, then I will have half half, then I will have half minus half, and then I will have 3 by 2 minus half, then I will have 3 by 2 minus 3 by 2. So, this is the lowest possible state, this is the highest possible state. Lowest possible state, I can have maximum M value as 3 by 2, and here you can see the maximum M value, that is M1 plus M2 is 3 by 2. Here the maximum M value is half, and this will also give me half. So, here M is 3 by 2, here M is half, here M is minus. So, this will give me, I have a plus here, because otherwise I will not get a minus half, these are repeated. So, here this will give me minus half, because minus 1 plus half will give me minus half, this will be also minus half, and the last one is the lowermost state, which is minus 3 by 2. Okay. So, now next step to proceed would be that you will have first term. Okay. So, there is only one way, or the answer to this we know is 1. So, CG coefficient of this would be 1, because here capital M or M is m1 plus m2 and this is the only possible state, and same holds for this last term, the lowest possible state. So, these two corners you are done, and the corresponding terms here it is not possible to have this 3 by 2 combination anywhere. So, you will have 0, 0, 0, 0. Same way I cannot have 3 by 2 in these. So, I will have a 0, 0, 0, 0 and 0. Now, corresponding to this half state there are two possibilities. So, let me call this as A and this as B, and it is not possible to have these. Similarly, I can have half with these two states. So, let me call this as C, this is as D. So, the remaining would be 0. Again here there is a minus half. So, these are all 0, here also these will be 0, these will all be zeros. But here minus half there are two possibilities. So, I can have a prime, B prime, here I can have a C prime, D prime. So, this is the table we have prepared using the ladder operator and orthonormality condition. You can evaluate these boxes, that is this matrices or the elements of these matrices, that is A, B, C, D, A prime, B prime, C prime and D prime. You have seen it for half cross half. Same way we are going to do it in this table, we are going to fill it. But before we go to anything, let us see here that this is a 1 cross 1. Very neatly you can see the table can be actually compactified as well as spread out as this is 2 cross 2. So, you have a block diagonal form 1 cross 1, 2 cross 2, here you have again 2 cross 2 and here you have 1 cross 1. So, this is a matrix 1 plus 2 plus 2 plus 1. So, it is a 6 by 6 matrix, and now you understand that you can first write the table and then evaluate these terms. So, coming back to the evaluation part, first term you have seen here, I have written down that the first term, that is 3 by 2 comma 3 by 2 is, this is the uncoupled basis, the coupled basis, and you can write this in terms of the uncoupled basis, correct. So, this is what we have, this is 1, from the table I can write this, agreed, correct. Now, in order to write this state 3 half, I can write it as 3 and half, 3 by 2 and half as A times this plus B times this term, agreed. So, let me write it. So, 3 by 2 comma half is written as A times 0 half plus B times 1 minus half, agreed. Now, in order to come from this state to this state, what we will do here is we apply a ladder operator, do a ladder operation. So, when you apply a ladder operator on J minus, that is J minus on this, you will obtain the CG coefficient C minus, and this state will be lowered by, that is M will be M minus 1. When you are applying your J minus here, your J minus here is, you will have to apply J1 minus plus J2 minus. This is what you are going to do in this step. So, when you do this, this term is very easy to check. Okay. This is very easy to check because you can easily calculate the coefficient of this. This will come out to be 3h cross 3 by 2 and half. Okay. And similarly, you need to calculate this part of the equation, and this comes out to be 0 half plus h cross 1 minus half. Alright. I am going really very slow so that you are not stuck anywhere, and then later you can actually do things much quickly, in a much smarter way actually. So, from this actually you can read the value of a and b. So, when you take this half here and cancel the h crosses, what you obtain is the value of a. So, let me write the value of a for you. So, it comes out to be 2 by 3 in the square root of 2 by 3, and this comes out to be 1 by root 3. Okay. Now, using orthogonality condition, you can obtain the values of C and D. So, use orthogonality condition. It is very simple to check, and why we are using orthogonality condition? When you operate this on any of the other quantities 1 or minus half or 0 and half, you will obtain the value of C and D, because again you will, or you can put this 3 by 2 half and half and half. When you do the use the orthogonality condition and use these two equations, you will be able to evaluate C and D. So, I leave it to you all to do this part to evaluate C and D. In similar manner, we can obtain A prime, B prime, C prime and D prime. So, these are all DIYs, do it yourself problem. Okay. So, this I think you will be able to manage this part of the problem. Now, again you may be bored, but it is very important to go to the next problem, because in the next problem J1 is 1 and J2 is 1. So, here the dimensionality has increased, that is you are going to a bigger and bigger matrix. Once you are comfortable with 4 cross 4, you can do this 6 cross 6, then you are going a step further wherein you have a 9 cross 9 matrix. So, when J1 is equal to 1, J2 is equal to 1, your capital J can take value 0 and 0, 1 and 2. Okay. And here again you will see how your M1, M2. So, your M1 will take value 1, 0, minus 1, M2 will take value 1, 0, minus 1 and so on. So, this will be again you can solve this very neatly, and you can actually obtain a 9 cross 9 matrix. Again you can guess from the previous question that it will be of the form 1 cross 1. The block diagonal form will be 1 cross 1, 2 cross 2, 3 cross 3 and 1 cross 1. So, 1 plus 2 plus 3 plus 2 plus 1. So, this will be a 9 cross 9 matrix. And one more thing is important here to note, that you can actually calculate this part of the matrix where you will take m positive m's only. Take positive m values, and the negative m values or the will give same result as positive m values. Remember this. Okay. So, negative m values will give the same result as positive m values. So, you can actually DIY this. Okay.